So hello everyone, my name is Clayton Kelly. I'm a senior at IUI, and I'm going to talk to you today about my project, which was in numerical simulations of deterministic and stochastic proportional dynamics. Those are scary math words, so we're going to go ahead and catch you all up with some background. So, deterministic versus stochastic dynamics. Essentially, when we're talking about dynamics, we're saying we've got a system, some sort of collection of objects that is evolving, usually with respect to time. In this case, it's also with respect to time. And we're trying to track how that system changes in regards to its variables, right? In a deterministic system, all of the variations and changes in our system can be fully known. Essentially, they're functions without randomness. So if you gave me enough information to start with, I could, in principle at least, predict every possible outcome of the system. In a stochastic system, which stochastic is basically just a fancy word for random, those variations may be functions of random variables. Or in other words, without a specific realization of random noise, for example, such as the random noise shown in this graph, I wouldn't be able to tell you anything about the outcomes of the systems. I might be able to bound it within some sort of random variations, but generally I wouldn't be able to tell you anything for sure. For example, in here, we can see all these little bounces and peaks and troughs in the noise data. That would be affecting, for example, the output measurements of our system. And so the question is, how do these random fluctuations create effects in our system? And the system we studied in particular, called the Cooper-Smale system, you can see it introduced here as a system of differential equations, is introduced in the early 2000s as a model for bird flocking, or more generally for any system where you have agents interacting under something that could be modeled as a force without any sort of hierarchy, right? There's no like queen bird or president bird or anything like that. They just sort of follow each other and go with the flow, and eventually that flow happens to work out for them. And so other applicable cases are listed there. If we wanted to give a name to this system, it's a homogeneous system of nonlinear differential equations, complete with a term here, which we typically call the communication rate, that models how these birds sort of don't want to crash into each other, but also don't want to get too far apart from each other. Essentially, it governs how these birds are going to interact with each other. The x's will represent positions, the v's will represent velocities, lambda and n are just parameters of the system, right? And then stochastic terms are what we're introducing here to better model real-world uncertainty. So the traditional system is deterministic in the sense I introduced on the last slide. But what we're doing is we're looking at this system here, which has been formed into matrices for convenience of reading. This is a velocity matrix, position matrix, where now we have this noise term dw with this rescaling term theta that depends only on the positions of the birds. And this is going to better model real-world uncertainty. Essentially uncertainty in, for example, measurements of the bird's positions, but also just random noise in the environment of the birds, which I'll talk about later. Prior works, not done by me, have shown that in the deterministic and the stochastic case both, it's possible to show that flocking occurs. Think of a flock of birds in your mind, no fancy mathematical definitions needed. You know what we're talking about here. They're all not infinitely far apart, and they're flying with essentially the same velocity and direction, right? And in both cases, it's actually possible to guarantee that flocking will occur under certain stipulations on the initial conditions. You can come check out my poster for more details, but essentially it's to do with the initial positions, the velocities, and the communication rate law. So what I did is I worked in the deterministic and the stochastic case to get numerical simulations. In other words, we can't really solve this system analytically, so we're going to ask the computer to do it for us. So what I did is I used MATLAB to do a simulation of the trapezoidal method, which is shown right there, for anyone that wants the gory details. And what we did is we essentially distributed particles normally in the position and velocity spaces. And what this allows us to do is sort of infer the behavior of nearby particles that we didn't exactly simulate, because we unfortunately cannot simulate infinitely many particles. But if we toss out enough particles, I can say, well, as long as you're close enough to one of the particles I actually simulated, this is roughly what's going to happen. And so we see that this is the velocity space. All of the birds' velocities are sort of converging to some common value here in the middle, and they're spreading out here in space. That's one possible simulation. There are other possible simulations that you can, again, come see with my poster. The poster one, I have videos on my iPad. But essentially, this is the kind of simulations we're looking for. And we analyze the numerical stability of these simulations. In other words, how accurate are they to what actual solutions of the system would look like. And in the deterministic case, the trapezoidal method is known to be astable. Basically, that's a condition to do with the system we're analyzing here, which our condition is satisfied. And we have order 2 convergence as exemplified by this log-log plot, where the slope of this plot tells us something about the convergence of our system. In particular, we converge quadratically as we decrease the time steps. So we get quadratically closer and closer to the actual solution as I make my time steps smaller and smaller. In the stochastic case, we have to consider what kind of noise we're talking about. We're talking about environmental noise, which essentially means it's independent of the agents and also independent of the communication rates. Think of, for example, like a sudden gust of wind at one particular spot as the birds are flying, right? That's not something that's accounted for typically in the model, but via random noise, we can take care of it. We also consider mostly uniform noise across agents. Essentially, that's the difference between these two graphs here. This graph is displaying uniform noise because as we see all of the processes, although it looks like there's only one, they're actually all just sitting on top of each other. Whereas here, this would be non-uniform noise across agents. Each one individually gets its own random variable. And what that does, really in the limit, it doesn't do much to the system because all of those random fluctuations sort of cancel each other out in the long term. Whereas this is going to have some actually noticeable effects on this slide. Here we can see that as we simulate the system, notice how it's not converging to one fixed velocity in the middle of the graph like it did in the deterministic case. Here that middle is sort of bouncing around. That's the effect of our random noise. Essentially, our random noise is pushing the center of mass of the velocity system in space. And so what that's having the effect of causing this bouncing behavior. In the non-uniform case, essentially what we observed is this bouncing on a path level, which didn't have any effect on the actual mean of the system, because in a long time, we couldn't really tell the difference. We simulated this using the implicit Euler method for stochastic differential equations, which again, for those interested in the gory details, is right there. And we maintained the same normal distributions as in the deterministic case, because it allows us to draw those comparisons like I just made, right? In the deterministic case, we saw sort of converges to a fixed velocity, whereas here that sort of convergence is bouncing around just. And here we again still see spreading out in the distribution of the position space, right? We also analyzed the numerical stability of our model in this case. The implicit Euler scheme is astable still, which again is nice. It means we're going to actually converge to genuine solutions of this equation, but it generally only has strong order of convergence of 0.5. I have to say strong in the stochastic case because there's actually two different kinds of convergence. For those interested, strong refers to convergence of the paths. Essentially, are we simulating the paths correctly? Whereas weak convergence corresponds to the convergence of the distribution. Essentially, are they ending up in roughly the correct configuration? We care about strong convergence. We're talking about the actual flight paths of these birds or whatever agents you may have. So usually you can only get 0.5, but because of the nice symmetries of our system, we can actually obtain higher order convergence. This is due to some properties of the matrix M that I showed all the way at the very beginning. Again, you can talk to me in my poster if you want more of the gory details there. But essentially, each of the rows sums to 0, and all of its eigenvalues are negative, or non-positive. They can be 0. And so essentially, what happens is the stochastic error in the implicit Euler simulation actually drops out, and so we only accumulate error in the deterministic term, and that leads to convergence of order 1 when that rescaling term theta happens to depend on the positions, and order of convergence 2 when we happen to have a rescaling term that is constant, right? And so lastly, I'd like to give some acknowledgements to Jeffrey Kwan and Constantina Trevisa, who were my advisors for this project, as well as Daniel Serrano, the Trend program lead, as well as all of my Trend, Grad Math, and Math Quantum colleagues for making this just a generally wonderful summer. Thank you all.